good sugar chemistry out there. All right, so Chemistry 3111, we're going to start the second half of our lecture on carbohydrates by looking at reactions of monosaccharides. And if you look at a monosaccharide, and here they have the pyranose form of glucose shown here. So we have beta D glucopyranose. What do you notice about this compound in terms of its functional groups? Well, if you said, well, jeepers, Mr. Dion, there's a lot of hydroxyls in this compound, you'd be absolutely right. And remember that we defined carbohydrates as being polyhydroxy aldehydes or ketones. And as you can imagine, since they have so many hydroxyl groups per carbon, you can imagine that they are going to be water soluble. So water soluble. But if you think about the chemistry lab, okay, if you think about things that you do in the chemistry lab to purify or to separate compounds, things like recrystallization or maybe TLC, or another technique that we don't do in our lab called column chromatography, those methods are used to separate organic compounds. So if you think about a TLC that you've run in the lab, what kind of solvents did you use to run a TLC? Dichloromethane, ethyl acetate, hexanes, things like that. And so those are organic solvents. And so it's pretty difficult to run a TLC or to purify a compound that has so many hydroxyls on it. So what you want to do is, if you want to make or render your monosaccharide so that it will be soluble in an organic solvent like ethyl acetate, so this is an abbreviation for ethyl acetate, or hexane or dichloromethane, what are you going to do? You convert all of those hydroxyls to esters. And the way you would do that is you would treat it with acetic anhydride. So that's what AC2O is. That's acetic anhydride. Again, we looked at that in the carboxylic acids in their derivatives chapter. And then PY, of course, stands for pyridine. So instead of using acetic anhydride, there's other techniques where you can use things like acetyl chloride, but whatever. So we take acetic anhydride, we use excess. Why? Because we have 1, 2, 3, 4, 5 hydroxyls. So we put it in excess. We treat that with pyridine, and we end up acetylating, doing what's called acetylating all of those hydroxyls. And you can see that we have 5 acetyl groups on here. And what that does is it renders it soluble in an organic solvent. And then our book doesn't talk about what you would do to remove those, but then you could remove those, after you've purified it. So again, the reason why you would want to make this, is so that you're able to purify it in an organic solvent, and then you would just pop those off. And if you're wondering, are there other groups that I could use besides an acetyl group? Okay, there's all kinds. You could use a benzyl group and remove it by hydrogenation. But again, what you need to understand is that you're starting it with something that's water soluble, highly water soluble, so difficult to purify in an organic solvent. You basically convert it into something that's soluble in an organic solvent so that you can purify it easily, and then you could remove those in the end. Again, our book doesn't discuss how to do that. You just have to know this reaction. All right, what else? We can convert those hydroxy groups into ethers via, hey, there's an old chestnut, the Williamson ether synthesis. So you remember the Williamson ether synthesis? It's where we would take a hydroxyl, we treat it with a base, and then an alkyl halide, and we would do an SN2, and then, of course, form an ether. So if we start with beta D glucopyranose, or pyranose, however you want to pronounce it, and we treat that with excess iodomethane, and we use silver oxide as our base, so we end up forming the pentamethyl ether. So we basically convert all of those hydroxyls into ethers. Now you might be wondering, how come we don't use sodium hydroxide or sodium hydride or LDA? Well, the reason we use silver oxide as a base is because it's a mild base. And what you're going to see later on in this lecture is that if we take beta D glucopyranose, for example, and we treat it with a strong base like sodium hydroxide, that is not going to work, because we cause the molecule to undergo what's called epimerization if you just take a sugar and treat it with a strong base like sodium hydroxide. And we'll discuss in detail what epimerization is, and we'll take a look at that in detail. Okay, so that's how you make a methyl ether. Okay, and as you can imagine, this would also be soluble in organic solvents. What else? This is kind of a going back in time here and talking about hemiacetals and acetals for a second. Remember, the cyclic hemiacetal of a sugar or a hemiacetal can react with an alcohol under acidic conditions to form An acetal, this is an old reaction that we looked at a long time ago in this class. So we take our hemiacetal. Remember, a hemiacetal is like having a carbon that has, it kind of looks like it's got an alcohol attached to it and an ether attached to it. And then you react it with an alcohol and a catalytic amount of acid, and you end up forming an acetal. And then, of course, you end up losing water. Remember, in the first step, you don't lose water, but this is the second step, and you form water. The first step, what I meant by the first step is when you form the hemiacetal, you don't lose water. Anyhow, so acetals of sugars have a name. You've got to know that name, and that name is a glycoside, right? If we examine the anomeric carbon, what's it attached to? It's got a hydroxyl, and it's got an ether on it like that. So you can clearly see that that is a hemiacetal. When we treat that with an alcohol like methanol and hydrochloric acid, we end up getting a mixture of glycosides. And what do I mean by a mixture? We end up with both the alpha and the beta glycoside in this case. And you can see here that when the methoxy group is pointing down, that would be the alpha methyl or the methyl alpha D-glucopyranoside. And when the methoxy group is pointing up, that's the beta anomer. Okay, so we have a mixture of anomers. And again, those are called glycosides. And a glycoside is an acetal, right? Don't lose sight of that. A glycoside is an acetal. Let me prove it to you. Look at the anomeric carbon. It's got an ether attached to it, and it's got an ether over here attached to it. So we've gone from a hemiacetal to an acetal, and when we're talking about an acetal on the anomeric carbon of a sugar, it's called a glycoside. So we end up again with a mixture of alpha and beta glycosides. So what have we covered so far this morning? Let's back up a little bit. We've learned three reactions. First, we've learned how to acetylate or put acetyl groups on the hydroxyls of a carbohydrate using acetic anhydride and pyridine. So this is our first reaction. We've learned how to do a Williamson ether synthesis on a sugar. And again, instead of using a strong base like sodium hydroxide, we use a weaker base like silver oxide. And the third reaction that we've learned is how to make a glycoside. Remember that carbon, that anomeric carbon in a glucopyranose, okay, is a hemiacetal. But when we treat that with methanol and hydrochloric acid, we end up producing a glycoside. Again, the acetal of a sugar is called a glycoside, and we get a mixture of both alpha and beta. Well, let's look at the mechanism of that reaction. It's one of the few mechanisms that we look at in this chapter. And you think, well, you've got all of these hydroxyls on this compound, right? I have one here, I have one here, I have one here. What's so special about the anomeric carbon? Well, if you draw the mechanism, it reveals what's so special about it. After you've protonated the hydroxyl and converted it into a good leaving group, okay, you form not only a carbocation, but it's a resonance stabilized carbocation. And so that is why you're going to form your glycoside at the anomeric carbon, right? Anomeric carbon, or carbon number 1. Well, if you think about the second step, or the overall, second part of this mechanism, I guess. So after you've protonated it, you form the resonance stabilized carbocation. What do you notice about this carbon right here, okay, in this resonance structure? This is sp2 hybridized, right? And if that's sp2 hybridized, it's going to be trigonal planar. So it's flat. So that means that when methanol comes in and attacks, it could attack from the top face of the molecule, or it could attack from the bottom face of the molecule. Here are both of the mechanisms of the nucleophilic attack of methanol on the resonance stabilized cation. Now here they're showing it deliberately. They're showing it this resonance structure where the positive charge is on the oxygen instead of the carbon, to prove to you or to show you that this is planar, right? That's flat. It's sp2 hybridized. So if the alcohol attacks from the bottom face of the molecule, right? You see how it's attacking from the underside of the molecule? They even drew the arrow. See, it's going underneath like that. Okay, so if you're attacking from the bottom face of the molecule, that's going to cause the hydrogen to move up, and your ether bond is going to be on the bottom like that. And that's the alpha anomer. right? This is alpha. And if it attacks from the top, again, you can see it attacking from the top face here. Well, that's going to give you the beta enantiomer because it's going to push the hydrogen down like this, and then your methoxy will be in the beta or the equatorial position at the anomeric carbon. So here's the beta enantiomer. Okay, now that's a mechanism that you're responsible for. Again, it's one of the few mechanisms that we look at in this class. And we've already looked at the formation or the mechanism for the formation of an acetal from a hemiacetal. This is just, basically the same thing, but doing it with a sugar, doing it with a monosaccharide. All right, let's look at another reaction. I mentioned a word earlier on. I mentioned something called epimerization, right? Because when we talk about the Williamson ether synthesis, I said that when we did the Williamson, we used silver oxide as our base, right? Because it's a mild base, okay? Now, I said that if you were to take a sugar and treat it with a strong base like sodium hydroxide, there's a problem, okay? You cause the sugar to undergo what's called epimerization. And it says here, under strongly basic conditions, aldoses, and D-glucose is obviously an aldose. Aldoses undergo, so this is an undergo epimerization at carbon 2 via an enediol, which is kind of like an enol intermediate. You can see what's going on here, right? You have your sodium hydroxide. It's going to cause a tautomerization, right? What's tautomerization? It's the movement of a hydrogen atom and a pi bond, okay? So we cause a tautomerization here to form an enediol. Where does the word enediol come from? Well, you've got an alkene and you've got a diol, so that's not too hard to put together. Anyhow, so you form an enediol, but that can also undergo tautomerization as well. So that's the process that's occurring here. And if you need to, look up tautomerization, again, tautomerization, okay, in the first step to form the enediol, but then it retautomerizes, and when it retautomerizes in the second step, come on, okay, when it tautomerizes again, you had a certain stereochemistry here, okay, and then when it retautomerizes, you end up with racemization occurring at that stereocenter. So if racemization is occurring at one stereocenter, we call those diastereomers epimers. And if you're like, why couldn't you just call them diastereomers? Because all the chiral centers are the same here, but they're different here. That's what you taught me before, way back in chapter 5. You said, well, if you have everything the same, but then one different stereocenter, you would call them diastereomers. But we can go one better, and when we have a diastereomer that differs in its configuration at only one chiral center, this is called, or these are called epimers, is what I should say. So epimers. So again, we go from having R configuration here to having a mixture of R and S. So that's the problem, okay? This is why if you were to try to do a Williamson ether synthesis with glucose, right, which only exists partially in the open chain form, okay, but if you were to try to treat that with sodium hydroxide, you're going to get epimerization, and then you're going to end up with a mixture of products. So not really handy, and that is why you have to use silver oxide. All right, what about reduction? Chemistry 3111, in case you haven't noticed yet, is replete with oxidation and reduction. It's very important in this class that you understand all kinds of oxidation reactions and all kinds of reduction reactions. So if we take a monosaccharide, which we know can exist in the open chain form, we can reduce the aldehyde of an aldose with sodium borohydride, right? And sodium borohydride can work in a polar product solvent like water, and you reduce that to what's called an alditol. So you need to know what an alditol is. So in the formation of an alditol, all you're doing is you're taking the aldehyde group of the aldose and you're reducing it to an alcohol. That's it. Okay? So now you have no aldehyde in your final product at all, and it's called an alditol. So you take glucose and you convert it to glucitol. And glucitol has a common name that you've probably heard of before. It's called D-sorbitol. In foods, we just call it sorbitol, and it's used as a sugar substitute in processed food. So reduction of an aldose to an alditol. Can you guys see my screen now? Sorry about that. Come on, buzz off. Just give me 2 shakes of a lamb tail. Can you see my slides now? Can everybody see my screen now? All right, good. Thanks, David. See, senor. Okay, good. Sorry about that. The joys of teaching remotely. All right, I guess I could put my iPad on airplane mode, right? Anyhow, where the heck was I? So sorbitol, which is used as a sugar substitute. You've probably seen that on packages of processed foods before. All right, so that's reduction of an aldose. What about oxidation? Well, it says here that aldehyde oxidation of an aldose produces an aldonic acid. So an aldonic acid, we're going to learn about an aldonic acid and an alderic acid. So I'll teach you my method for remembering which one is which. Aldehyde oxidation of an aldose produces an aldonic acid. There's a whole holy host of oxidants that you can use to affect this transformation to convert the aldehyde to a carboxylic acid. But if you're thinking like, oh, come on, Mr. Dion, like you're doing an oxidation and you're not going to oxidize all these hydroxyls, you're not going to oxidize a hydroxyl. Well, these are very specific conditions, and I've never done this reaction before, but I know that these are really sensitive conditions. So it says here bromine and water in a pH of 6. And the mechanism isn't covered in our textbook. If you wanted to look it up, be my guest, but it's not covered in the in ACS, and it's not covered in our textbook. But you have these very mild conditions. So basically, when you make this solution of bromine and water and you have the pH buffered to around 6, what it does is it will react with an aldehyde, but it won't react with an alcohol. Pretty cool, huh? Anyhow, so again, very sensitive conditions, and maybe it has to be fine-tuned depending on the substrate, but I'm sure that this reaction is, well worked out a 100 years ago, probably. So you buffer that just right at a pH of 6, and you can oxidize the aldehyde selectively to carboxylic acid that we call gluconic acid. If it's glucose, you replace ose with onic acid, and we call that an aldonic acid. So that's another reaction that you need to know. But there's all kinds of oxidations that we do of aldoses. And in fact, that reaction, okay, if we go back here, what it's talking about is this reaction here with the whole, we'll write it down here. So bromine in water at a pH of 6. So if I copy this, that set of conditions for oxidation, come on, how do I paste? There we go. Yeah, this set of conditions for oxidation is very selective. Okay, it'll selectively oxidize an aldose, but not a ketose. And it can actually be used as a chemical test to differentiate between the two. Because if you go back to what I said in the previous lecture, I said, well, come on, an aldose and a ketose, there's an equilibration, right, where the ketose can undergo equilibration to produce an aldose. Okay, but under these conditions, it will not do that. Okay, but there are other conditions that we can use, other tests, and you might want to read this in the textbook very carefully. It says your oxidation tests are also performed to detect the presence of a reducing sugar. Okay, whether it's a pyranose or a furanose form of a sugar. So going back again to the last lecture, I said that a ketose was a reducing sugar. Okay, I said that an aldose, or maybe I didn't, but anyhow, an aldose or a ketose can be a reducing sugar. So what's so special about these conditions, okay, is that it's going to oxidize the aldehyde, but not the ketone. Now, other oxidizing tests here, okay, are what oxidize both an aldose and a ketose. And examples of those would be the Tollens test, the Failings test. I don't know why I didn't put this in here. The Benedict's test. I'm going to go in and edit my slides because Benedict's test is important. Now, if you're wondering, what are you talking about here, Mr. Dion? What's this whole test thing that you're talking about? Okay. So back in the day, long time ago, before you and I were ever born, okay, before chemists had things like IR and NMR, they had it was a lot more difficult to determine or to elucidate the structure of organic molecules. So if they had sugars and they wanted to determine their structure, they couldn't just, go into the lab and run an NMR or run a IR. They had to figure it out, kind of the hard way. And one of the ways that they were able to detect whether they had a reducing sugar, so an aldose or a ketose or a glycoside, okay? So this is what these tests are for, or they would be to distinguish between an aldose or a ketose versus a glycoside, okay, is if they treated it with the Tollens test. The Tollens test is where you take silver ions and you reduce them, okay? So a reducing sugar is going to be a sugar that's going to cause the reduction of silver plus to silver zero. And silver zero is silver metal. So what happens is when you take a reducing sugar, again, an aldose or a ketose, you have a sugar. You don't know what it is. You're like, is this an aldose or a ketose? Or is it a glycoside, okay? An acetal, okay? If you want to determine, is it an aldose or a ketose or a glycoside? You mix it up with the Tollens reagent, which is the Tollens test. If it forms a silver mirror on the glassware, so literally a mirror that you can see yourself in, that's a positive test. That means that the sugar reduced the silver plus ions to silver zero ions. In the process, of course, the sugar was oxidized, and we're not worried about that, but that's a proof that you had either an aldose or a ketose. Same thing applies to Benedict's and Failings tests. In both of those, you start with copper 2, which is it's got like a blue color, like a Windexy, blue solution, okay? The color of blue Windex. I guess there's different colors of Windex now. But anyhow, what happens is when you reduce copper 2, so copper 2 plus, to copper 1 plus, copper 2 plus is blue, okay? And when the copper is reduced by the aldose or a ketose, which gets oxidized, it forms copper 1, which is like a brick red color, okay? So if you had a red precipitate formed, which is copper 1 oxide, anyhow, if you form a red precipitate, that would mean that you have an aldose or a ketose, okay? If you got no reaction, then you'd say, well, I probably have a glycoside, okay? Again, there's so many chemical tests that were used back in the day, and we don't learn all of them, but we do learn a few of them that are really important. In fact, in the lab, we still use these with students. Okay, when I teach chemistry for nursing students, we do all of these tests. In fact, the Benedict's test was used to monitor the glucose levels in patients' urine. I mean, it's a long time ago. Now we have more sophisticated ways of doing that, but they could basically, treat the urine with the Benedict's reagent, and they compare it on a color chart, and they could, quantify to some degree how much glucose was coming out of a patient's urine. Anyhow, kind of interesting. All right, let's talk about some more oxidations. We already talked about the oxidation to an aldonic acid using bromine and water at a pH of 6. If you use a stronger oxidant like nitric acid, it's going to oxidize the aldehyde and the primary alcohol. Remember, all of these are secondary alcohols here, so it's going to oxidize that and the primary alcohol of an aldose to form an alderic acid. So you're going to oxidize again the aldehyde and the primary alcohol, and you form two carboxylic acids, and that's called an alderic acid. The way that I remember aldonic acid, so you get aldonic acid, and then you have alderic acid. Is I compare the letters N and R. So aldonic acid and alderic acid. So N comes before R in the alphabet. So N is only the oxidation of the aldehyde. So one group is oxidized, and then alderic acid, you oxidize both the aldehyde and the primary alcohol. I don't know. That's the way that I do it. So again, we treat our aldose, our glucose, or any other aldose with nitric acid, water, and we cook that up and we form an alderic acid. It says here, a mild oxidizing agent must be used to avoid the oxidation of everything. So all of these conditions that we're learning today for oxidation, these have all been carefully worked out by many chemists over a long period of time. Yeah, that's enough information. All right, last couple reactions that we're going to learn in this section 24.6 deal with altering the carbon skeleton of our sugar. You guys probably remember cyanohydrin formation. This is something we looked at way back in chapter 10, cyanohydrin formation. So if you take an aldehyde, treat it with hydrogen cyanide, you end up forming a cyanohydrin. So this is a cyanohydrin here. But remember, this carbon here is sp2 hybridized. Therefore, it is planar. And so the nucleophile is going to be able to attack from either side. And you end up with a mixture of stereoisomers at this chiral center here. Now, the Killiani-Fischer synthesis takes that cyanohydrin. Look, what have you done? You've added a carbon to the molecule. Look, here you have one carbon, and you add a second carbon. So in the Killiani-Fischer synthesis, the cyanohydrin is hydrolyzed to a carboxylic acid, and then it's subsequently reduced to an aldehyde. Now, that's the old way, okay? Now we have a better way of doing it. I haven't even looked at the Killiani-Fischer synthesis, the old version, in a long time, but I know it's, a few steps. So you take that all the way to a carboxylic acid, and then you reduce that to an aldehyde. But nowadays we have a more modern method, but we still call it the Killiani-Fischer synthesis, and it's a two-step procedure. In the first step, you just treat it with hydrogen cyanide in order to form your cyanohydrin. But then in the second step, you take that cyanohydrin, and the nitrile undergoes a hydrogenation to form an imine, okay? And since it's in water, so this is all in the same step. This is part of number 2, okay? It gets hydrolyzed to form an aldehyde, okay? So what it does is it lengthens the carbon chain of the sugar by 1 carbon. I can guess what a lot of you are thinking already is, okay, I see that you're lengthening the carbon chain, but if you had, if you knew all the other chiral centers, all of a sudden you racemize. You form a mixture of epimers. That's true. It's true, but it doesn't mean it's not useful. Here's overall what the reaction would look like. So let's say we took D-arabinose. Again, I wouldn't expect you to memorize the name of D-arabinose, but if you take that in the first step, treat it with hydrogen cyanide, you form the cyanohydrin, right? That's in the first step, cyanohydrin. And then we treat that with hydrogenation conditions using palladium. Remember palladium on carbon? Well, here we're putting the palladium on barium sulfate, and we're doing the reaction in water. And again, that hydrogenation in barium sulfate produces the imine, which is hydrolyzed to produce the aldehyde. But again, you end up with epimers, and we could even write that down here. So these are diastereomers, but remember, since they only differ at 1 chiral center, we call these epimers of each other. And as far as how you would go about separating D-glucose and D-mannose, It can't be easy. Cannot be easy. I'm not even sure how you would do that. If you do some kind of chiral column or something, there's got to be a way. Anyhow, next is the Vole or the Vole or the Vole degradation. So it achieves the exact opposite of the Kiliani-Fisher, right? In the Kiliani-Fisher synthesis, we were lengthening the carbon chain by one carbon, but here we're shortening the carbon chain by one carbon. So this is a three-step, okay, three-step synthesis. So the Vole degradation is 3 steps. It's a little steppy, right? First step is to treat it with hydroxylamine. So this is called hydroxylamine. And then you form an oxime, which we looked at earlier on in this class. So after you form the oxime, you treat it with acetic anhydride. You end up losing water, and you form the cyanohydrin, and then you treat that with sodium methoxide in the last step, and you end up losing cyanide, okay, in the last step, and you would lose a carbon, okay? So what's kind of cool here is that you could actually start with a pair of epimers, and you would only end up with one compound. Okay, and if you're wondering, what do you mean by that exactly, Mr. Dion? Well, we're going to look at some examples that will prove that to you. So the Vole degradation. Okay, so now we're going to look at some problems. So this is slide 41. Let me just go all the way to the end. Okay, this is the very end. So now it's 8:35. You've covered all of the reactions that you need to know in this chapter. Okay, the first one we learned was acetylation to form esters, right? And that makes it easy to purify. So that's acetylation is the first one. Then we looked at alkylation, which is, just a variation of the Williamson ether synthesis. So an alkyl halide, like methyl iodide, and a mild base like silver oxide. Again, if you were to try sodium hydroxide, you get epimerization. Next, treatment with an alcohol and an acid to form an acetal, which we call a glycoside, right? It's got a sassy name. If we do a reduction of our the aldehyde on our aldose with sodium borohydride and water, we can reduce the aldehyde to form an alditol. So we form an alditol. Then what's next? We learned how to selectively oxidize the aldehyde to make an aldonic acid. And then we learned how to oxidize both with nitric acid, water, and heat to form an alderic acid. So here we have an are they on here? Oh yeah, reduction to form an alditol, and then to form an aldonic acid, oxidize, and then we oxidize to form an alderic acid. There we go. So those are all the reactions that you learned, and that's all the reactions for this chapter. If you're thinking, well, it's enough for me. Yeah, I know. All right, well, let's try some practice problems, and then this should hopefully clear some things up. If you're confused about any of these, okay, where was I? Look at my notes here. Okay, let's see. Question 24.27 says draw and name the structure of the aldohexose that is epimeric with D-glucose at each of the following positions. Let's start by drawing D-glucose. If you did some practice over the weekend, you might have this one memorized by now. I'll draw it as neatly as I can. So there we go. So we have a hydroxyl here. We have another one here. Oops. There we go. All right, like that. Then we fill in our hydrogens. And since we're asked to draw the epimer at both carbon 2 and carbon 3, let's number our carbons. So we start with the most oxidized as being carbon number 1. So that's 1, 2, 3, 4, 5, and 6. All right, so we have both of those. And if we want to epimerize at carbon number 2, that means we're just going to reverse that chiral center, right? Because epimers are diastereomers that differ at only one chiral center. And so we could even just, I could even just do this, couldn't I? I could just, come on, there we go. I could just paste this back in here, couldn't I? Yeah, there we go. And then, oops, we'll just reverse that. So get this out. There we go. So we're just going to reverse at that center. So we have a hydrogen here and an oxygen there. There we go. And if we go into the list of sugars, which I had in here somewhere. So again, I will provide whatever you need. But if you look, it's this sugar right here, which is D-mannose. Let's go back to our slides. Let me find it. Did that get deleted? Are you kidding? Oh, good. So this is D-mannose. Okay, so from now on, I'm not going to refer back to that handout of the family of aldoses and ketoses. I'll just, yeah. So now we're going to take this guy and we're going to paste it again. Okay, and then we're going to epimerize at carbon 3. So we're going to swap carbon 3. So let's do that. We'll erase this, we'll erase that. And when we epimerize at carbon 3, we end up with this, where all the hydroxyls are on the right-hand side. And this is D-allose. D-allose. All right, give me a thumbs up if you think you can nail that one. If you're like Mr. Dion, just make a whole quiz of this. I'll destroy this thing. I'll obliterate it. All I had to know was what a epimer is. Is anybody with me? All right. Thanks, David. Good. So good. Is there something wrong with my chat? Okay, there's something wrong here. Try this. Okay. Can the quiz just be this? Sorry, Skylar. The powers that be wouldn't be very happy with me if I made the quiz just that. But there you go. You can see, it's a pretty reasonable question. Let's try another one. 24.28. Trust me, Skylar, this question is just as simple as the last one. It says the same product is obtained whether D-altrose or D-talose is treated with sodium borohydride in the presence of water. Explain. Well, let's draw D-altrose and D-talose. So D-altrose is this. I need a new prescription. I cannot see very well, but let's go for it. So D-altrose is this. Just want to have a hydrogen here. So, son of a gun. There we go. There we go. So this D-altrose, and then we'll draw D-talose down here. The hardest part is drawing the sugars. Okay, so now we have them both here, and we're going to treat both of them with sodium borohydride in water. And what are we going to form? We're going to form an alditol, aren't we? So sodium borohydride in water. And we're going to reduce both of the aldehydes, right? We're going to reduce this aldehyde and this aldehyde. So let's draw the product. Might be faster if I just use the copy-paste tool. So I'll copy this guy. So copy. I'll paste this. I'll reduce that aldehyde to an alcohol. So now I have CH2OH. Then I'm going to do the same thing with my D-talose. Let's move this up a bit. There we go. So I'll copy this. There we go. And now we're going to reduce that aldehyde as well. There we go. Okay. And it says here the same product is obtained whether you reduce either D-altrose or D-talose. Well, hopefully you can see that if you were to take, if you were to take this and rotate it 180 degrees, 180 degrees rotation, you would end up with this compound, right? They're identical. So structures are identical. All right, there we go. Give me a thumbs up if you follow me on that one. I don't think there's a way for me to rotate that, is there? No. Anyhow, yeah, Abby says cool. I agree. It is pretty cool, isn't it? You end up with the same darn molecule. Remember, this is something I was going to say. I stopped myself, but I'll say it, okay? Remember, with sugars, you can rotate, right? You can take this guy and you can spin it around. Where's my pen? Okay? You can take a sugar and spin it around and around and around and around and around. That doesn't matter. That's not going to change anything. But you cannot flip them like a pancake, okay? You cannot put a pancake flipper under. This is a pancake flipper. You cannot take that and flip it, okay? That's a big no-no, okay? Why can you not flip it like a pancake? Well, the reason why is because, remember, all of these bonds are coming out, right? These are all coming out, and all of these ones are going back in the page. So if you flip it, they're all reversed. So you can't just go ahead and compare structures that way. All right? Anyhow, but rotation is fair game. Okay, so we end up with we end up with two alditols, and they're the same. So we'll write that down here, an alditol. Okay, there we go. Let's try another one. 24.30 of the 8D aldohexoses, only 2 of them form optically inactive alditols when treated with sodium borohydride. In the presence of water. I see. Identify these 2 aldohexoses and explain why their alditols are completely optically inactive. Well, remember from the last problem that when we take, an aldose and we treat it with sodium borohydride and water, we end up reducing what? We reduce the aldehyde to an alcohol. Well, with that in mind, let me do something I said I wasn't going to do and go back to this guy here. So if you look at all these compounds, all the aldohexoses, there's 8 of them. Okay, if we look at all 8 of these, now I'm not going to draw all 8 of them out, but if you were to convert these aldehydes, if you were to reduce all of those to CH2OH, can anybody tell me which one of them, and there's 2 of them here that will produce compounds that would be optically inactive? They will not rotate plane polarized light. I'll give you a second to look at it and see if you can figure out which ones. Can anybody figure out which ones might reduce to give you something that wouldn't rotate plane polarized light? So this would be a compound that has symmetry in it, right? Let's think about it. If I was to take D-allose, right, and if I was to treat this with sodium borohydride and water, okay, in water, what would I end up with? I end up with this alditol. So I have, and look at this, even though I have 4 chiral centers, okay, there are 4 chiral centers in this molecule. What else do I have? Look, I have a plane of symmetry running down the molecule like this. So I end up with a meso compound. So that's not going to rotate plane polarized light. And so one of the answers is D-allose. Is there another one on here? It's not going to be idose, because if you reduce idose, you're not going to have a plane of symmetry running down the molecule. Okay. What about galactose? If I do the same thing with galactose, if I treat that with sodium borohydride and water, what do I get? I get CH2OH. Remember, it's got to have a plane of symmetry. In D-idose, you don't have symmetry going down the molecule. So 1, 2, 3, 4, like that. I'd have 4 chiral centers, right? But then I have a plane of symmetry running down the molecule right here, okay? With D-idose, you would not have a plane of symmetry running down the molecule. And so the answer is D-galactose and D-aldose. So let's just go back to the slides and I'll just pencil that in. Where was I? So the answer was D-allose and D-galactose. Galactose. There we have it, folks. All right. Determine whether each of the following compounds is a reducing sugar. In order for a sugar to be a reducing sugar, it has to be reduce. Okay, that means it can reduce silver plus ions or copper 2 plus ions, right? It can reduce these to silver 0, and it can reduce this to copper 1. Okay, well, in order for it to do that, it has to have a hemiacetal. So must have a hemiacetal. All right. Well, with that in mind, let's take a look at A. Would A be considered a reducing sugar? Yay or nay? Anybody? Anyone? No, I'm going to say no, right? Because it is a glycoside, right? The anomeric carbon has an ether here, and it has another ether here. So this is an acetal. It's not a hemiacetal. So no, the answer to the next one is yes, because we have a hemiacetal. Look, we have an alcohol here, and we have an ether here. So this is a hemiacetal. And the last one is also a big resounding yes, right? Because the anomeric carbon has a hydroxyl attached to it, and it has an ether. So same reason, this is a hemiacetal. So all you have to look for is that if you have a hemiacetal, it's reducing sugar. If you have an acetal, it's not a reducing sugar. Nothing more than that. 23.34 says, draw and name the pair of epimers that are formed when the following aldopentoses undergo a Killiani-Fischer chain lengthening process. Let's just try A. Remember, the first step is to treat the molecule with hydrogen cyanide. The second step is hydrogen palladium on barium sulfate in water, so you can hydrolyze the imine in situ. And what are we going to draw? Now we're going to go from having an aldopentose to an aldohexose. So we're going to draw, we're going to have CH2OH. We have our aldehyde at the top. We have 1, 2, 3, 4. The bottom 3 remain unchanged. That's going to be the same as these 3. Oops. And so we'll put 3 hydrogens here and 3 hydroxyls here. Okay, I'm going to copy this. I'll paste it here. So we're going to end up with epimers at that position. So we're going to have one where we have the hydroxyl here and one where we have the hydroxyl on the other side. So that gives us D-allose when we go look at the chart. And then this is D-altrose. So allose and altrose. If you do the exact same exercise with the next one, I deleted it. Okay, if you try the same exercise, okay, with the other sugar, what are you going to do? You're going to end up having a chiral center here, right, and adding an aldehyde on the top of it, and that will give you a mixture of D-gulose and D-idose. All right, so we'll just do do that one for now. Let's try 24.38. This deals with the Vole degradation. It says when D-glucose undergoes a Vole degradation followed by a Killiany-Fischer chain lengthening process, a mixture of two epimeric products is formed. Identify both epimers. So let's start by drawing D-glucose. So we'll start with 1, 2, 3, 4. So here we go. So this D-glucose. So D-glucose. Okay, let's do a Vole degradation to start with. So the Vole degradation starts with hydroxylamine in the first step, followed by treatment with acetic anhydride in the next step, followed by treatment with sodium methoxide in the third step. What are we going to do? We're going to lose the carbon from the aldehyde, and we're going to end up with an aldopentose instead of an aldohexose. So we'll draw that out. So we have CH2OH. We have 1, 2, 3. Okay. And then we're going to have this guy. Looks like this. Okay, so we did the degradation, right? We lost the chiral center. And now we're going to lengthen the chain using the Killiany-Fischer synthesis. So first step is going to be hydrogen cyanide. Second step is going to be hydrogenation conditions with palladium on barium sulfate in water. And then we're going to end up with a mixture of epimers. And so I'm going to not only end up with my starting material by D-glucose, I'm going to end up with this. I'm kind of running out of space here, aren't I? Plus, I'm going to end up with its epimer. Shoot. Let's see if I can move this stuff up. I'm also going to end up with the epimer at carbon 2. There we go. So if I draw the epimer at carbon 2, I just switch these. I end up with a hydroxyl here and a proton here. And I end up with D-mannose. Okay, there you go, D-mannose. Give me a thumbs up if you think you can nail that one. Vole degradation followed by a Killiany-Fischer. You know, it's a good exercise, but the only question I have is when I look at this problem, I'm like, why? Why would you do this? I guess the only reason I could think of why you might do this would be if you needed D-mannose and you only had D-glucose, you end up with a 50-50 mixture. I don't know. Whatever. All right, let's move on and talk about disaccharides. So we only have a few minutes left, but the last two sections are really quick. So you have to have a few disaccharides memorized. Disaccharides consist of two sugars connected through a glycosidic linkage. The glycosidic oxygen connects carbon 1 of the sugar on the left. So when we write out disaccharides, we always go from left to right, to carbon 4 on the sugar on the right. So this is a 1,4 disaccharide. So you see that maltose is made up of 2 glucose units. It always has an alpha 1,4 linkage. That is, okay, so we'll put here linkage. Linkage is alpha 1,4. Okay, and sometimes we write 1-4. Sometimes they write it with a little arrow like that. There's all kinds of different ways that are written. See, it says a 1,4 alpha glycoside. So here's my glycosidic bond right here. So this molecule that's written here, maltose, is always going to have an alpha 1,4 linkage 100% of the time. Since this hydroxyl is pointing down, this would be called alpha maltose. Maltose. If the hydroxyl at the anomeric carbon was pointing up like that in the up position, it would be beta maltose. Okay? This is something that students get confused on sometimes. But remember, maltose is always going to have this alpha 1,4 linkage. Cellobiose and maltose only differ by the stereochemistry at the anomeric carbon. So that's why that linkage is so important that you understand that with maltose, it's an alpha glycoside, meaning that the 1,4, the bond coming off of carbon 1 is pointing down, okay? And cellobiose is a beta glycoside because the bond coming off of the anomeric carbon to form the glycoside is pointing up. Okay, so cellobiose is always going to have this linkage, and maltose will always have that linkage. Again, what's drawn here on the slide, since this hydroxyl is pointing down, this is alpha maltose, is what you would call that. And since the hydroxyl is pointing up here in the cellobiose, you would call this beta cellobiose. Cellobiose. All right, so you need to know that maltose is made of 2 glucose units and that cellobiose is made of 2 glucose units, but their linkages are alpha 1,4 and beta 1,4 respectively. Lactose is another disaccharide. On the left-hand side, we have galactose, and on the right-hand side, we have glucose. You need to know that the linkage is a beta linkage, right? Because the glycosidic bond is formed from the anomeric carbon of galactose, and it's going in the up position. Now, again, since the hydroxyl on the anomeric carbon of glucose is pointing up, I would call this beta lactose. Beta lactose. If it was pointing down, it would still be lactose, but it would be alpha lactose. So maltose and cellobiose, both made from glucose, just different linkages. Lactose made from galactose and glucose, and it has a beta 1,4 linkage. Another disaccharide that you need to know is sucrose. Sucrose is just plain old table sugar. Honeybees can convert sucrose into a mixture of sucrose, fructose, and glucose. I don't know if I'd ever ask anything about what honeybees can do, but you need to know that sucrose is not a reducing sugar. There is no hemiacetal present. So no hemiacetal. Okay, if you look at the anomeric carbon here, you can see that you have an ether here, and you have another ether here in the glycosidic bond. If you look over here, you can see this carbon is attached to a carbon. Okay, it's got an ether here. It's got another ether here, so no hemiacetal there. There's no hemiacetal anywhere in this molecule. You can examine it from here till Friday, but you'll never find a hemiacetal. If you look at lactose, lactose is a reducing sugar. Why? You can see it's got a hemiacetal right here. Cellobiose is a reducing sugar. It's got a hemiacetal right here. Maltose is a reducing sugar. It has a hemiacetal right there. So they all have hemiacetals. And so the only non-reducing disaccharide that we're going to look at is sucrose. Only one. Determine whether each of the following disaccharides is a reducing sugar. So all we have to do is look for a hemiacetal. If there's a hemiacetal present, you, my friend, have a reducing sugar. Okay? Another way of saying, is there a hemiacetal? If I look at the first one and I look at this carbon, you can see that it's attached to a hydroxyl and it's attached to an ether. That's a hemiacetal. So I would say, yes, this is a reducing sugar. Okay? If I look at the next one, if I look at this carbon or either of these anomeric carbons, you can see that here I have an ether. Here's my glycosidic bond, so that's an acetal. And since I have an alkoxy group here, this is also an acetal, right? I have an acetal there, and I have an acetal here. I have no hemiacetal, and so the answer is no. If I look at the last one, it's sucrose. We've already looked at sucrose, and we said that sucrose has no hemiacetal, and therefore it is not a reducing sugar. There you go. That covers all of disaccharides. Let's move on to polysaccharides. Cellulose is a polysaccharide. Probably the most, I think it's the most abundant organic molecule on the planet Earth. Cellulose is a polysaccharide containing 7,000 to 12,000 glucose units connected through beta glycosidic bonds. What would be the disaccharide, from cellulose would be cellobiose, right? Anyhow, or cellulose, it's found in, wood and plants. So, things like wheat and grasses and trees and everything. So you can imagine that's why, or it's pretty obvious why cellulose is the most abundant organic molecule on Earth. Yeah, so you can see that the linkages, the glycosidic bonds, again, are beta 1,4 linkages. It says here beta. We could even write in here beta 1,4 linkages like that. The cellulose strands strongly hydrogen bond with one another, giving wood and plant materials the rigid structure. So if you draw out a bunch of cellulose units, you can see how they're actually really, they have a linear form to them, and it enables them to hydrogen bond really strongly with one another. Anyhow, cellulose can be spun into fibers. It can be made into wraps like cellophane or a piece of paper. Cotton, for example, is almost pure cellulose. And again, it's the most abundant organic compound on the planet. All right, let's move on from there. Starch looks similar to cellulose because it's a polysaccharide that's made up of glucose units. Again, if we go back here, cellulose was made up of glucose units. What's the difference between starch and cellulose? It's the linkage, isn't it? If you look at the linkage in starch is what? It's alpha 1,4 linkages. There are two components to starch. There's amylose and amylopectin. Yeah, so the branching in amylopectin. So amylose is just all linear, like is shown here on this slide. Amylopectin has branches off of these hydroxyls right here, which are about 20 to 25 units. And this is the glucose storage form in plants. Whereas glycogen, so if you've heard of glycogen, glycogen is very similar in structure to amylopectin. The only difference is the size of the branches. Glycogen's branches are more frequent and they're shorter. So here's the branches off of C6. Again, if you look at the branches on glycogen, they're just more frequent and shorter, nothing more than that. All right, well, that covers all of the carbohydrates chapter. We're not going to cover section 24.9 or 24.10. So here's a review of the reactions. We looked at how to draw a pyranose or a chair form, a chair pyranose form of an aldose. Again, I'm not going to ask you to do that for a furanose. I won't ask you to draw a Haworth projection from a ketose, but I will ask you to do this because we went over in detail in the first lecture. Here's the reactions of monosaccharides. I've already covered these in detail with you. And we also learned the Kiliani-Fisher synthesis. So here's the Kiliani-Fisher reaction. And then this is the Vole degradation right here. And that's it. That covers the entire chapter from soup to nuts. Who wants to try some practice problems? I think it might be a good idea. Try a few. Yeah, let's go for it. So here we go. So here's some practice problems. Again, these are posted to Canvas. I'll post the solutions soon, and they're also available in the chat. Is anybody there? Students there? It's hard to say. I can't see who's online, when I have my slides pulled up. All right, good. All right, you get two people. Let's go. So we're going to try these practice problems. All right, good. Great. So I'll give you a second to think about the first one. I'll be right back. All right, who's got an answer for the first one? Plants convert CO2 and water into glucose in the presence of sunlight via... All right, thanks, Winona. Photosynthesis. Number 2, a monosaccharide with 5 carbons in a ketone functional group. So if you've got 5 carbons in a ketone, this would be a... Yep, ketopentose, exactly. Let's move on to the next one. Which of the following is an aldohexose? Well, it's got to have an aldehyde in it. So it could be either this one, or this one. It cannot be this one or this one because this is a ketose, and this is a ketose. Okay, and then we have to have how many carbons? If it's a hexose, we need 6 carbons. Here we have 1, 2, 3, 4, 5. So we can cross this one out. Here we have 1, 2, 3, 4, 5. So we can cross that one out. Here we have 1, 2, 3, 4, 5, 6. And so the answer is D-glucose. All right, let's move on from there. I'll give you a second to look at the next few or the next couple. Anybody have an answer for number 4? Yeah, Winona's correct. She says constitutional isomers, right? Because D-glucose is an aldose, and D-fructose is a ketose. So they're not enantiomers, they're not epimers, they're not anomers, they're not diastereomers, but they both have the same molecular formula, don't they? They both are C6H12O6. Because D-glucose is an aldohexose and D-fructose is a ketohexose. And so they are constitutional isomers of each other. Which of the following compounds are mirror images, are enantiomers of each other? Getting ahead of myself here. So we're looking for non-superimposable mirror images. I'll give you a second to try to find out which ones are which. Yeah, Winona's got it. It's B. Number 2 and number 4. So if you look at these ones, maybe if I put them in a box, it'll be easier to see. But you can see that these are, right, this chiral center is reversed, this chiral center is reversed, this one's reversed, and this one's reversed. So we'll put here all chiral centers have opposite configuration. All right, there we go. Sorry about the interruption there. My brother was trying to call me on FaceTime. Anyhow, look, it's 9:13. I think it's better probably if you try these practice problems by yourself. For the lab data sheet, is it fine? Sure. Yeah, if we didn't crystallize the product in 3112 in the video, yeah, just leave them blank. It's no problem. So I'll post the solutions to the problems for this data, or for this problem set, and the quiz will be on Wednesday, and I'll provide an announcement about that and exactly which structures you can bring into the quiz room with you. All right. Well, I'll see you on Friday for the lecture on amino acids, peptides, and proteins.